As I mentioned before, when it comes to the phase behavior of a mixture, in order for that solution to be stable in a homogeneous phase, the criteria for that is that the second derivative of the Gibbs energy of mixing has to be positive, right? So that would tell you that the system, is at a minimum, right? Related to that, we could define when a system becomes unstable by looking at the conditions at which its second derivative changes signs. So it corresponds to point where second derivative changes sign, right? Or in other words, the second derivative of delta G mixing is equal to 0. Okay? To kind of visualize what's going on, we could return back to this figure here, okay? Where, in the delta G mixing curve, we see that the curve has some sort of bump on it, right? And so, because this curve has a bump, or essentially a maximum, we see that in this region, the curve is concave down, right? So, right here, figure shows, and where it becomes concave down, the points that are marked A and B here, because originally it goes from concave up to concave down. So that means there must be some point here in which we have an inflection point, essentially, right? And so A and B mark that inflection point. So figure shows inflection points on each side of bump where delta G mixing is concave down. Okay? Right, and so we'll refer to those as XA dagger and XA double dagger. Right, so those are the compositions that correspond. So let me erase this. Correspond to the inflection points. Okay. All right. And so within that range where delta G mixing is concave down, we would say that those compositions refer to the unstable region. XA values where delta G mix concave down corresponds to unstable region. Okay? All right. And so what we mean by unstable region is, if you visualize the curve here, let's say your solution starts out at this composition, right? Any small change in XA would knock the solution to a lower entropy of mixing, or Gibbs energy of mixing state, right? Very easily. It's not well supported by the shape of the curve, so it's just going to fall down. Okay? And so small changes in XA will knock delta G mix to lower values, causing phase separation to occur immediately. Alright, and so in this unstable region, when the system phase separates, I'll say that it phase separates by a mechanism known as spinodal decomposition. Where it just phase separates very quickly. We won't talk about the details of spinodal decomposition. That's sort of outside the scope of the class. But just know that this means it happens very quickly. Okay. Alright, so that's what happens when you're in the unstable region. Let's now talk about if you're in the region between x prime, x dagger, and x double dagger, and x prime. So in the region where the curve is still concave up, but we're not at these sort of places where the chemical potentials are equal. Okay. Alright, so XA values between XA prime and XA dagger and XA double prime and XA double dagger, we call that the metastable region. Okay. And so here, if you're in this region, you're not stable, but you're not unstable. And so what that means is that only large composition fluctuations in the mole fraction, or large changes, in other words, knock your delta G of mixing to lower values. Right? And so when we're in this sort of region, phase separation occurs via what we call a nucleation and growth mechanism. Right? And so compared to spinodal decomposition, this form of phase separation is relatively slower. I won't call it slow because, on the time scale of an experiment, it can happen very quickly. But at least compared to spinodal decomposition, this sort of mechanism is slower. Okay? All right? And so that's, at least how we could think of. So I'll mark it here in color. This is unstable. And these regions are metastable. So that's how we would visualize it on the delta G mixing curve. But if we go back to the phase diagram, right, and we look at the binodal and spinodal portions, and we'll talk about how to calculate the spinodal in a bit, it's a little bit easier to visualize what's going on. And so in the region directly under the spinodal, this is the unstable region, right? And in the regions between the binodal and the spinodal, this is the metastable region. Okay? And so if your composition is initially here, you're going to phase separate very quickly into the coexistence curve. But if your initial composition is here, it may take a while for you to actually undergo the phase separation and reach equilibrium. Okay? Alright, so now as far as how to calculate the spinodal. So, to calculate spinodal, you'll need some sort of model for your delta G mixing. So we'll start with the regular solution theory. Okay. And what we need to do is we need to take the second derivative of it. So, of the Gibbs energy. So we take the second derivative of the delta G mixing, and I'll divide it by kBt just to kind of simplify things out. And that's okay to do because we're taking the second derivative with respect to the mole fraction. Okay? So we'll take the second derivative of this, 1 minus xa, ln of 1 minus xa plus xa, 1 minus xa, chi ab. Alright, if we go through that derivative, second derivative, we get this. Alright, and in order to find the spinodal, we need to find the inflection points, right? So that's where the second derivative is equal to 0. So we're going to set this equal to 0. Therefore, we get this equation. Xa squared minus xa plus 1 over 2 chi ab is equal to 0. Alright. Let's write this a little cleaner. Alright, and so in order to calculate the spinodal, you essentially just need to solve equation 2 here. Alright, and so the steps for finding spinodal: define spinodal. What you want to do, once again, you vary your xa values, then calculate your equation 2, or actually before doing that, calculate your delta G mix, and then based on your delta G mix, if you see that there's a concave down section, or in other words, your delta G mix has a bump, you want to then solve equation 2 to get your xa dagger and xa double dagger. Alright, so once again, by solving this equation here, you would do it at all the different temperatures. Solving that equation, you could get the two spinodal compositions there. And then you just repeatedly solve that equation for all the temperatures that fall below, or in which, that fall below the critical point temperature. Okay?